Welcome back to Engineering Systems. In this explainer, we're diving right back into the architecture of FoodDash. Over our last few topics, we've explored how to make systems way more reliable by eliminating those pesky single points of failure, adding failover, and we even conquered the famous nines of availability. So the engineering team is feeling pretty good right now. Honestly, the system is far more resilient than it used to be.
But then something kind of strange happens. A junior engineer walks into a team meeting and asks a super simple question. Hey, if every single component in our system is 99.9% available, doesn't that mean FoodDash as a whole is also 99.9% available? Everyone nods. It seems completely reasonable, right? Actually, scratch that. It is totally wrong.
Okay, so let's dive into exactly why. Imagine a very stripped down, simple version of FoodDash. A customer opens the app, the request goes over to an API server, that API server talks to a database, the database returns the information, and boom, the customer sees the restaurant menu. Now let's assume the API server is 99.9% available and the database is exactly 99.9% available too. At first glance, you'd think the whole FoodDash system should naturally hit that exact same target. But here is the catch. For that customer's request to actually succeed, the API absolutely must be working, and the database must be working at the exact same time. We need both, not either, both. Think about what happens in the real world when a hungry customer opens FoodDash. Let's say the API is healthy, great, but the database happens to be down. Well, the request fails. Now imagine the reverse scenario. The database is totally healthy, but the API server just crashed. The request fails again. For the customer, it literally doesn't matter which piece of the puzzle failed. The result is the exact same frustrating experience. They can't order their food. This kind of dependency chain is what we call a series system. In a series system, a request has to successfully pass through every single component in the chain. And if even one link in that chain breaks, the entire request fails. Your architecture is fundamentally only as strong as its weakest link. So let's make this a little more realistic and see what happens as FoodDash grows. Because it's not just an API and a database anymore. We now have a load balancer, an API service, a database, a payment service, and a notification service. Suddenly, that request path looks a whole lot longer, doesn't it? And here's the scary part. Every single component we add introduces another opportunity for failure.
Which leads us to a surprising and honestly kind of hidden discovery. As FoodDash adds more features, sure, it becomes a more powerful app, but it can actually become less available. Suppose every single component is 99.9% available. That's almost perfect. But put 4 or 5 of those components together in a chain and your overall availability becomes lower than any individual component. It's not dramatically lower, but it is lower. The more dependencies you string together, the more your overall system availability slowly gets chipped away.
This right here is one of the biggest hidden challenges of distributed systems. Modern applications aren't just one monolithic thing. They are complex collections of services. So the absolute crucial takeaway is this. Every dependency adds capability, but every dependency also adds risk. We obviously want a powerful application, but we absolutely don't want our availability moving in the wrong direction.
So how do we fix that? Well, that brings us to parallel systems and redundancy, or basically creating alternative paths. Let's go back to our database layer for a second. Instead of just one database, let's say FoodDash now has 2, a primary database and a replica database. This is the real aha moment. A customer's request no longer depends on one specific database. Instead, we've created multiple paths to success. If database A fails, no big deal. Database B can just take over, and the system keeps right on humming. In a series system, remember, every component must work. But in a parallel system, you only need one healthy path. A great way to think about this is using a simple river crossing analogy. A series system is like having exactly one bridge. If that bridge collapses, you are completely stuck. There's no way across. But a parallel system gives you 2 bridges. If one is closed for repairs, you don't panic, you just simply take the alternate route. You still get to your destination. And suddenly, all of our past topics connect together perfectly. Why do we replicate databases or add redundant servers? We do it to create parallel paths. Tech companies literally spend millions of dollars building these alternative networks and multi-region data centers because parallel systems dramatically improve uptime. The entire goal is to reduce the number of components that absolutely must work and increase the number of ways a single request can succeed. To quickly recap our core lesson today, when you connect components in a series, every single one of them must be healthy, which unfortunately decreases your overall availability. But when we build redundant infrastructure in parallel, only one path needs to work. Redundancy essentially transforms those fragile series chains into highly available parallel systems, building your uptime right back up to where it needs to be.
Now, fixing this creates another totally fascinating question to leave you with. FoodDash now has multiple healthy, redundant servers just waiting in parallel to take those alternate paths. But if there are 4 healthy servers waiting for traffic, how exactly does the system decide which one handles the very next request? How do we make sure one doesn't get completely overwhelmed while the others just sit there idle? Well, that is exactly what we're going to explore next time as we dive into the magic of load balancing. Thank you for watching Engineering Systems. Make sure to subscribe so you don't miss the next episode in our Availability Pattern series. See you then.